All right. Hello and welcome to the last section that we're going to work on in differential equations. This section is going to take 2 days to go over just because it's so long to actually get to a solution. So today I'm just going to do the first 3 pages. Tomorrow I'll do the last 2 pages. But talking about solving homogeneous linear systems, we're going to talk about using the eigenvalues. So if we let A be an n by n matrix and a number lambda is said to be an eigenvalue of A if there exists a non-zero solution vector K of the linear system. So again, the K is going to be a solution to our differential equation, but the K cannot be like the zero vector, cannot be, the 0, 0. And so if that's the case, then there is going to be some, scalar that's going to be an eigenvalue that when we multiply that eigenvalue times our, solution, then it's going to be equal to our matrix times our solution. And so what we call that is we call that the lambda. And if this occurs, then the solution vector is said to be an eigenvector corresponding to the eigenvalue lambda. So a lot of what we're going to do today is we're going to find how can we find lambda and how can we find the eigenvector, because if we can find these, then we can find solutions to the differential equation. So the first thing that we want to do is we want to verify that 1, -1 is an eigenvector of the matrix. It's K, all right? And our matrix is 2, 3, 2, 1. So we're just going to put it into our form, AK equals lambda K. And A is a 2, 3, 2, 1 matrix. Our eigenvector is 1, -1, so our K is 1, -1. And then we're going to just put that into equals lambda K. Now, on the left-hand side, we're going to go ahead and multiply. We're going to multiply our 2 by 2 times a 1 by 2. So we should get, 2 by 2 times a 2 by 1. So when we do that, we should get a 2 by 1. So we multiply 2 times 1, 3 times -1, add the 2, we get -1. And then to do the second row, we're going to do 2 times 1 and get 2, and 1 times -1, we get -1. 2 minus 1 gives us that 1 right there. So all I did to get this is I went ahead and multiplied AK. And there's the work for that. Now, that's equal to the right-hand side. All right, some lambda, the eigenvalue, times 1, -1. Now, when I look at this, is this possible? Can the left-hand side equal the right-hand side? Yes. If lambda equaled, all we got to do is change the values. If lambda equaled -1, then it would work. So this is an eigenvector because there's an eigenvalue that when I multiply the solution vector, I get A times the solution vector, or the matrix times the solution vector. So therefore, 1, -1 is an eigenvector, and our eigenvalue to make that happen is just -1. All right, so how can we, on our own, find eigenvalues and eigenvectors? Well, it can be a very long process. Not too long if it's a 2 by 2 matrix, but if we're dealing with a 3 by 3 matrix or a 4 by 4 matrix, it could be very long. Now, if you have taken, and some of you have already taken linear equations, then you can use the methods that you were taught in that class to find solutions to a system of equations. You actually might have learned that in math analysis way back when you took that. But that's finding like row reduced echelon form and using your graphing calculator to find those solutions. All right, so how do we find them? Well, I'm going to set up my solution, my formula at the top, which is AK is equal to lambda K. And I'm going to set that equal to 0. So I'm going to move my lambda K over to the right. If I do that, I'm just going to subtract. Now, I technically cannot do that the way that is. That operation, I'm not allowed to do AK minus lambda K. Because A is an n by n matrix, and lambda, that's just a scalar. So I cannot subtract that unless, right now I can do it, but I want to pull a k out. If I pull a k out, I cannot do a minus lambda, all right? I cannot have that form right there because a is a matrix, lambda is just a scalar. So how can I pull out a k and still be able to subtract? I'm going to put in the identity matrix. If I put in an identity matrix, then when I multiply by lambda, remember the identity matrix is 1, 0, 0, 1. When you multiply by the identity matrix, you're not changing really anything. It's like multiplying by 1 in a typical algebra problem. So I'm able to multiply by the identity matrix so that I can go ahead and subtract those two. So that's why it's a minus lambda I, so that I can subtract the two. And now I'm going to base everything off of that to find my eigenvalues and eigenvectors. So the first thing that we want to do is we want to find the determinant of a minus lambda I. Once we find the determinant, we're going to set that equal to 0 and we're going to solve. Once we solve, we'll be able to find what our eigenvalues are. After we find our eigenvalues, we're going to plug those back into the left-hand side, and we're going to set that equal to 0, and we're going to solve. So let me show you what I mean. We're going to find the eigenvalues and eigenvectors of matrix A, which is a 2, 2, 1, 3. All right. So we have the determinant of a minus lambda I. So that's the first step. We're going to find the determinant of our matrix minus our eigenvalues times the identity matrix. Now again, this lambda I is just lambda 0, 0, lambda because it's the identity matrix. So anytime we're doing the determinant of a minus lambda I, you're going to have a diagonal. It's just going to be, whatever that first value is minus lambda, whatever that, diagonal from that, which is going to be 3, it's going to be 3 minus lambda. And as you go along the diagonal, you're just going to subtract the lambdas. Everything else pretty much stays the same. Notice the 2 and the 1 stay 2 and 1. Alright, now we're finding the determinant. So we multiply 2 minus lambda times 3 minus lambda. We get lambda squared minus 5 lambda plus 6, and then once we multiply that, we're going to subtract 2 because 1 times 2 is 2, so minus 2. Now let's go ahead and put this, solve this, so simplify it, so we just subtract the 2 to get the plus 4. So lambda squared minus 5 lambda plus 4 is quadratic. I can factor that and get lambda minus 4 and lambda minus 1. So I found my two eigenvalues. It's lambda is 4 and lambda is 1. So we have two of those, so I have a sub 1 and a sub 2. Let's plug in the lambda sub 1. So if we say lambda sub 1 is equal to 4, we're going to go ahead and now plug this back into this form. A minus lambda I k equals 0. Hopefully you notice this is always going to take the same shape as kind of, what we originally did for the determinant. We're going to do 2 minus lambda, but lambda's 4, so it's 2 minus 4. You notice the 2 and the 1 stay the same. And then we do 3 minus lambda, so 3 minus 4 times our k and set that equal to 0. Right, so hopefully you're saying, okay, that's not too bad. Now, we're going to make this a linear, we're going to set these up as a system of linear equations. So what's 2 minus 4? Well, that's negative 2. And then we just put the k sub 1 there. And then we have 2 there, so plus 2k sub 2. So that's our first equation. Our second equation is 1 times k sub 1, which is k sub 1. 3 minus 4, which is negative 1, so minus k sub 2. Set that equal to 0. So there's our system. So now that we have our system, I'm okay with you going straight from this part right to that part. You don't have to show, all this. I just showed this because these are notes, and I want you to see how we got our system of equations. So, hold on, I went too far. All right, because I don't know why I boxed that up. All right, so we solve this system. You should know how to solve systems of equations. You've worked on that since Algebra 1. So you should know how to do that. When we solve, we know, oh, hey, I get really 0 equals 0. So when I look at this, I'm going to realize, oh, well, since these are opposite, it's really k sub 1 is equal to k sub 2. So therefore, I can make this eigenvector 1, 1. I can make it 2, 2, 3, 3, 4, 4. Doesn't matter. I can make that, any number, but I want to keep it simple. So I'm going to make it 1. I don't want to make it a number that's going to be more difficult to work with further down the line. So we got our eigenvector for the first one for lambda sub 1 is equal to 4. Now let's find it when lambda sub 2 is equal to 1. So we plug that in. Same thing, 2 minus lambda. And then keep the 2, the 1, 3 minus lambda. Put that into a system over here. So we have our system. 2 minus 1 is 1, so it's k sub 1 plus 2, k sub 2, 0. K sub 1 plus 2, k sub 2, 0. Hopefully you notice, those are the only two that are going to be different. All the other ones, those are going to be the same. Okay, so it's not going to be, it's not designed to be that complicated when we move on to another one. So now when we have this system, we solve. When we solve, we get k sub 1 is equal to negative 2 k sub 2, and then k sub 2 is equal to, and then we can say k sub 2 is equal to 1. We could say k sub 2 is equal to 2. We can make k sub 2 be whatever we want. We could have made k sub 1 equal to whatever we want. Again, we want to keep this simple. So what we'll do is we'll say, we don't want to do 0, 0 because, you don't want that as your kind of your solution vector. So let's make this, let's say k sub 2 was 1. If that's k sub 2 is 1, then k sub 1 is going to be negative 2. And there's our eigenvector. So there we have 2 eigenvectors and we are finished. We found our eigenvectors and our eigenvalues. All right, so how can we find a solution? Well, if we're given, x prime is equal to ax, so we have a differential, in this case, system. Can we find a solution of the form x equals k sub 1 all the way to k sub n e to the lambda kt, which is equal to our eigenvector. So this k is our eigenvector times e to our eigenvalue t. So it's going to be a solution. So each eigenvector and eigenvalue are going to give us a solution to our differential equation, and it's going to be written k e to the lambda t. Now, say we have a bunch of lambdas, all right? So distinct real eigenvalues. Let n be distinct eigenvalues. So all of our eigenvalues are different. I'm going to pause here and make this the second video.